So what is the second law of thermodynamics? And how does a heat engine work? What is a refrigerator? These are the questions in this edition of the video. Before we get to the second law of thermodynamics, we need to look at what a reversible process is. There are two types of processes, reversible and irreversible. A reversible process can be retraced exactly passing through the same states in the indirect process as in the direct process. So here is an example. The system goes from A to B, passing through intermediate states C and D. If the system can be retraced from B back to A, passing through the states D and C, then it's a reversible process. And in order for a system to be a reversible process, it has to be really slow. So slow that we call it a quasi-static process. So in this example, ACDB, BDCA is a reversible process. The system goes from state A, passes through C, D, gets to B, and it can be retraced from B through D, C, and A. That's a reversible process. But in an irreversible process, the system goes from A to B along this path, but when it goes back to A, it passes through some other states, for example, E, and gets to A. So we say ACDB, BEA is an irreversible process. Really, all processes in nature are irreversible. Well, we can approximate many to be almost reversible, but in practice, they are actually irreversible processes. So now let's look at the second law of thermodynamics. The second law of thermodynamics is the principle of the heat engines. And according to the second law, if we put a cold object and a hot object in contact with each other, heat will spontaneously flow from the hot object to the cold object. Without us doing anything, it'll go by itself from the hot to the cold. But if we want to transfer heat from the cold to the hot, then we have to input work. It will not spontaneously flow from the cold to the hot. So that's the second law of thermodynamics. So here is a statement. It's impossible to transfer heat from a cold to a hot object without the input of work. So how do we use the second law for a heat engine to work? In a heat engine, first of all, a heat engine is something that converts heat into mechanical energy. So heat energy is converted into mechanical energy. This is the idea of a French engineer called Carnot. So it's called Carnot's engine. And in the heat engine, there must be a source, which is a very hot object. There must be a sink, which is a cold object. And there must be a working substance, which is an ideal gas, which can take heat from the hot object, use a part of it to do work, and reject whatever remains to the cold object. So it takes heat from the hot object, converts it into work, and if anything remains, that heat is rejected to the cold object. So you can see that TH is the temperature of the hot object, QH is the heat absorbed by the working substance, W is the work done, QC is the heat rejected to the cold object, which is at a temperature Tc. So the Q stands for heat taken in and heat rejected. The T's, of course, stand for the temperatures in Kelvin. And work is actually QH minus QC. For example, if 1,000 joules of heat is taken from the source, from the hot object, and if 400 joules is given to the sink, that means 600 joules has been converted into work, right? So 1,000 is taken, 600 is converted into work, and 400 is given out to the cold object. So the work done is QH minus QC. The efficiency of any machine is the output divided by the input. In this case, the output is the work, because we're looking for work. That is the output, while the input is QH. Therefore, the efficiency of the heat engine is defined as work over QH. Let's get to that first, and then I'll explain the processes. So that's the definition of efficiency, work over QH. But since work is QH minus QC, efficiency can also be written as QH minus QC divided by QH, of course. In terms of temperature, efficiency can be written as 1 minus or TH minus TC by TC. I'm going to show how we get this formula from the definition of efficiency as work over QH. So that's going to come in a few slides. I'm going to show exactly how we go from here to this formula. Now let us look at the processes involved in a heat engine. A Carnot's engine is actually a 4-stroke engine because there are 4 processes in its working. Those are the 4 processes that are shown here. The first one, step 1, is isothermal expansion. Second is adiabatic expansion. The third is isothermal compression, and the fourth is adiabatic compression. So there are 2 isothermals and 2 adiabatics, 2 expansions and 2 compressions. So how it works is, first of all, you have the cylinder with a piston here, and here is the working substance, which is the ideal gas. And as heat QH enters the gas expands. So it actually does work. It expands. The piston is pushed out and the gas expands. But before the expansion can be completed, if the outside of the cylinder is completely insulated, you can see it's an insulation now. So that means there can be no heat coming into the system and heat cannot escape the system. So now the gas is still going to continue expanding because of the energy that it already absorbed in the previous process. But this is going to be an adiabatic expansion. Why? Because the system is not exchanging heat with its surroundings. In the third step, we have to now push the piston down. When I say we have to, an external agency has to push the piston down, thereby compressing the gas isothermally. So when we compress the gas, it gives out heat to the cold object. So heat QC is rejected to the cold object. But before the complete compression is done, we now insulate it and complete the cycle, bringing the piston back to its initial position from where it started. So if you look at this and you look at this, they are in the same position. So this is adiabatic compression. So when you look at the Carnot cycle, it becomes even more clear. Now let's look at the Carnot cycle, the pressure volume diagram. clearly shows the four processes. Mn is the isothermal expansion, where QH heat is absorbed. NO is the adiabatic expansion. OP is the isothermal compression, where QC joules of heat is given to the cold object. And PM is the adiabatic compression. So isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. So those are the four steps in Carnot cycle. And in order to find the useful work done in Carnot cycle, we have to find the area of this graph. So the area of this quadrilateral, so to say, would give you the useful work done, which is actually QH minus QC. So now let's try to get the formula for efficiency that I had promised you. In order to do that, we will look at this process, which is an isothermal. And we know that the work done in an isothermal process is nRT, natural log of the final volume by the initial volume. So the work done in this case is the same as the heat absorbed. Why? Because there is no change in internal energy. Why isn't there a change in internal energy? Since this is an isothermal process, its temperature doesn't change, which means its internal energy doesn't change. That means the heat absorbed is equal to the work done by the first law of thermodynamics. That's why we have QH is equal to the work, which is nRTH, natural log Vn by Vm. Remember that the temperature here from M to N is a constant, and it's TH. Similarly, during the isothermal compression, the temperature remains at Tc. And therefore, the work, or QC, is now nRTC, natural log VO by VP. Now notice that here it was the final volume Vn by Vm. Here it's VO by VP because it's a compression, okay? So we got that. So if you take the ratio of QH to QC, the terms cancels out, NR will cancel out, and we have this, TH, natural log Vn by Vm divided by that. Okay? Now let's look at the adiabatics. This is the equation for an adiabatic. Tv raised to gamma minus 1 is a constant. Let us apply that to the adiabatic at points N and O. What is the temperature at N? It is TH. What is the volume? It's Vn. So TH Vn raised to gamma minus 1 is equal to Tc, that's the temperature there, VO raised to gamma minus 1. That's what is written there. So now we can see that if you apply the adiabatic equation to points M and P, then at M, TH Vm raised to gamma minus 1 is equal to Tc Vp raised to gamma minus 1. If we divide the two equations, now divide this equation by this, automatically we see that the TH and TH will get cancelled here, TC and the TC will get cancelled there, and that means Vn by Vm would be equal to VO by Vp, because the raised to gamma minus 1 will also cancel out. So now look at that. So that means these two ratios are the same. Look. So in the natural logs cancel out. These two are the same. So we get QH by QC is equal to TH by TC, which is important. So the ratio of the heats is the same as the ratio of the temperatures. Therefore, efficiency can also be written as 1 minus TH by TC instead of 1 minus QH by QC. I hope that makes sense. So now let us look at the working of a refrigerator. First, the principle of a refrigerator. The refrigerator is actually Carnot's engine working in the reverse order. So now the working substance absorbs heat from the cold object, and when work is done on it, it rejects the heat to the hot object. So instead of going down, now it's going up. So heat is absorbed from the cold object, work is done on the working substance, and then it's able to transfer the heat to the hot object. So it's in line with the second law of thermodynamics, which states that if work is input, then heat can be transferred from a cold object to a hot object. So that's what you see here. Heat QC is absorbed from the cold object at temperature Tc. You see the arrow is in the opposite direction, so work is input or work is done on the working substance, and it's able to reject heat QH to the hot object at temperature TH. And when you actually look at a functioning refrigerator, on the right side, we see a compressor with the working substance, which in this case would be Freon. So as the piston comes down, work is done on the working substance, so heat is produced, number one, and number two, Freon gas now becomes a liquid because of the high pressure. And it's hot now, that's why it's red in color, and the heat of compression is given out into the room when Freon passes through the radiator fins. That's what this is called, the radiator fins. And then it reaches an expansion valve. On the other side so the expansion valve is a tiny orifice or a tiny hole. On the other side, the pressure is really low, and this side, the pressure is high. So when the pressure of the liquid now becomes really low, it turns back into a gas. So it turns back into a gas here. But in order for it to change into a gas, for any liquid to change into a vapor or a gas, it requires its latent heat. So it takes the latent heat from the food in the freezer while it passes through these tubes, as you can see. And then the gas returns to the compressor while the piston is going down. See that? So as the piston goes up and down, this cycle is repeated. So each time the liquid changes into the gas, it takes its latent heat from the food in the freezer, so the food gets cooler after each cycle. So that's the functioning of a refrigerator. And just like we define the efficiency of a heat engine, we are going to define the coefficient of performance of a refrigerator. It's not called the efficiency because this is a number which can be more than 1 or more than 100%. So it's called coefficient of performance. And the symbol is K sub R. Okay? So coefficient of performance, as you can see, is actually flipped. Instead of work over QH, it's QC over work. Two differences. It's QC over work. So similar to the other formula, we're going to get TC over TH minus TC. Even in this case, work is QH over QC here. So these are the two formulas for finding the coefficient of performance of a refrigerator. For a modern refrigerator, the coefficient values are between 6 and 7. Could be a little more than 7. Okay. So here is the cycle. If you look at the Carnot cycle, even that's reversed. Now you see that it starts from M, and instead of going this way, it's going from M to P, then P to O, O to N, and N to M. So you see that it's exactly the reverse cycle of a Carnot's engine. All right, so that is what you see. Number 3 is a heat pump. Now, what is a heat pump? The heat pump is what keeps us warm in winter. Like today, it's very cold outside, the heater is working. What is happening is gas is burnt and the heat produced is pushed out by the pump into the house. That's all. That's the heat pump. And the coefficient of performance of the heat pump is a little different. If you look, it's instead of QC by work, it's QH by work. You notice that? It's QH by work. And again, you will see the same difference when we define it in terms of temperatures. It is TH by TH minus TC. Again, here, work is QH minus QC. So now let us work out some problems. Here's the first one. A mole of ideal monoatomic gas at 0 degrees Celsius and 1 atm is warmed up to expand isobarically to triple its volume. How much heat is transferred during the process? So there's 1 mole of an ideal monoatomic gas. It's kept at 273 Kelvin because temperature's always got to be in Kelvin, and the pressure is 1 atm, which is 101,325 pascals. And this gas is warmed up. So that means heat is given to the gas and it expands how? Isobarically, means the pressure is constant, to triple its volume, which again means the ratio of the final volume to the initial volume is 3. We got to find how much heat was transferred during the process. I'm going to work out this problem in 2 different ways, just so you see the techniques involved. So here are the quantities. The pressure is 1 atm, which is 101,325 pascals. The temperature is 273 Kelvin. Then the number of moles is 1. The ratio of the final to the initial volume is 3. The formula for change in internal energy is 3 by 2 nR delta T. Now the 3 by 2 is because it's a monoatomic gas. If it was diatomic, it would be a 5 by 2. If it is triatomic, it would be 6 by 2. So here it's monoatomic, so it's 3 by 2 nR delta T. And by the ideal gas equation, we know P1 V1 by T1 is P2 V2 by T2. We know that. But the pressures are the same because it's an isobaric process. So P1 is the same as P2. We can cancel that out, which means that the ratio of the volumes is the same as the ratio of the temperatures, mathematically. And which is 3. So what I did is I just divided V1 by V2 should be T1 by T2. And because we know that, I divided V2 by V1. V2 by V1 is T2 by T1. And since we know that V2 by V1 is 3, therefore T2 by T1 should also be 3. Okay, so T2 is 3 times T1. And since we know T1 is 273, that gives us the value of T2 as 819 Kelvin. So now that we have both the temperatures, we can find the change in internal energy, which is 3 by 2 nR delta T, and delta T is the change in temperature. So 3 by 2 times 1, R is the universal gas constant, so it's 8.314, and the change in temperature is 819 minus 273. On calculating that, we get 6809.17 joules. So that is the change in internal energy. All right, what are we looking for? We're trying to find the quantity of heat transferred during the process. So V1 is 0.0224 meter cube. Why? 1 mole of an ideal gas, if kept at 0 degrees Celsius and 1 atm, will have a volume of 0.0224 meter cube. That is a standard. But we can get that value using the ideal gas equation, PV is equal to nRT, and substituting the values that are given. Okay, N is 1, so I've not written that. So that's R. T is 273, and the pressure is 101325, correct? And we will get this value. So we know the volume V1. Since we know the initial volume, we also know the final volume because it's 3 times the initial volume. And because we know the 2 volumes, we can now find the work done. Work done in an isobaric process is simply pressure multiplied by the change in volume. The pressure is 101325, and the change in volume is given there. So when you do that, you get 4539.44 joules. Okay, so we have the change in internal energy and the work. Now we can apply the first law of thermodynamics and find the quantity of heat. Let's do that. So according to the first law, delta E is what? Q minus the work. So Q is change in internal energy plus the work. We have both those quantities. Change in internal energy is here and the work is here. So all we got to do is add those 2 quantities and we will get our answer. So when we add those 2, we find that the heat that was transferred during this process was 11,348.5 joules. I hope that makes sense. Now we can do this in another way. Here is a second method of doing it. The specific heat at constant pressure is the specific heat at constant volume plus the universal gas constant. And since we know that for a monoatomic gas, specific heat at constant volume is 3/2 R, all we got to do is just add R to that and we would get this as 5/2 R. So that is Cp. Now once we know Cp, we know the formula Q is equal to NCp delta T. That gives us the quantity of heat that is given to the gas. So N times Cp is 5R/2 delta T. Okay, let's substitute the values. N is 1, so I've not written it there. And it's 5 times 8.314 into change in temperature because we already got that. So we are actually using that from the last part. 819 minus 273, and that will give us 11,348.6 joules. So this method is a little bit easier than the first method. But I wanted you to go through both of these processes, and I hope it makes sense. Shall we go on to the second one? Excuse me. Here is the second question. An engine with an efficiency of 0.30 absorbs 500 joules of heat per cycle. How much work does it perform per cycle? And how much heat does it reject per cycle? So this is a problem about Carnot's engine. The efficiency is 0.30 and it absorbs 500 joules, so that must be QH. So we have E is equal to 0.30. We have the heat absorbed, which is QH, as 500 joules. We are asked to find the work. Well, we know that work is related to efficiency by this formula. Efficiency is work over QH. So that gives, excuse me, 0.30 is equal to work over 500. Simple calculation gives the work as 150 joules. In the B part, it says how much heat does it reject per cycle, which is QC. So we're looking for QC. That's easy because work is QH minus QC. We have the work and we have QH, so not a big deal. QC is QH minus work, which is 500 minus 150. That comes out to be 350 joules. That's how we do that question. Number 3, it's a refrigerator. Now, a refrigerator discards 80 joules of heat per cycle. So words are important. Discard means to throw out or throw away. That means it's what? It's the heat given out. What is the heat given out called? It's called QH. Because it's a refrigerator, you have to remember that the heat taken in is QC, the heat given out is QH. So that's where you have to be careful. So what is given here is QH, because QH is the heat given away to the hot object. And the coefficient of performance is 6.0. What are the quantity of heat it removes per cycle from a cold reservoir? Okay, so we're looking for what? QC now. So QH is given 80 joules. The coefficient of performance is 6.0. And we're looking for QC. By the definition of coefficient of performance, it's QC by work. That is QC by QH minus QC, because work is QH minus QC. And then all we got to do is substitute and calculate. 6.0 is QC by 80 minus QC. We just got to be careful there. Cross multiply. So that's why the 80 times 6 becomes 480, and QC times 6 is minus 6 QC is equal to QC. Therefore, take this to the other side. You get 6 QC plus QC, which is 7 QC, is 480. So QC is 480 divided by 7, which is 69 joules. So that's QC. And in the B part, find the amount of work per cycle required for its operation. Oh, work is just QH minus QC. So that is simple. So work is QH minus QC. We have QH as 80 joules and QC as 69. So the work done per cycle is 11 joules. All right. Here's the next one. What is the minimum work required of a refrigerator if it is to extract 50 joules per cycle from the inside of a freezer? So extract means remove. So that means that is QC. Remove. So QC. And the temperatures are given. So the cold is at negative 10 Celsius and the hot is at 25. You got to change both into Kelvin, of course. We're looking for work. QC is what is given. It's 50 joules. So really what is important is to know whether what's given is QC or QH. And in order for you to do that, you should know how each one works. All right. TC is negative 10 plus 273, which gives 263 Kelvin. And TH is 25 plus 273, which is what? 298 Kelvin. We're asked to find the work. We will use the formula for coefficient of performance, which is QC by QH minus QC, which is also TC by TH minus TC. Remember that the ratios are the same, so use the 2 and then calculate. So 50 divided by QH minus 50 is equal to 263 divided by 298 minus 263. So on the right side, when you do the calculation, that comes out to be 7.5. And then we just got to cross multiply. So QH minus 50 times 7.5 is 50. And then when you do the calculation, you get QH is 56.7 joules. Of course, you got to distribute these two, multiply, and then do it carefully. You get QH is 56.7 joules. But we are asked to find the work. And what is work? Work is QH minus QC. We got QH and QC, take the difference. So that's 56.7 minus 50, which gives 6.7 joules. So that is the work done per cycle, okay? All right, I think this is the last question. An ideal gas at 300 Kelvin is compressed isothermally to 1/5 its original volume. Determine the entropy change per mole of the gas. I did not talk too much about entropy, but I just want to say that the change in entropy ds is dq by t. All right, so we're going to do that, but let's look at the question again. This is an ideal gas at 300 Kelvin, and it's compressed isothermally. What is an isothermal process? Constant temperature. So the temperature stays at 300 Kelvin, but the volume becomes 1/5 its original volume because it's compressed. We got to find the change in entropy. All right, so let's work it out. To find the change in entropy of this one, temperature is 300 Kelvin. The ratio of the final to the initial volume is 1/5. N is 1 mole because it says find the entropy change per mole. So N is 1 mole. And ds, which is the change in entropy, is what we're looking for. Here is the formula. ds is dq over T. Now, dq is the quantity of heat. It can either come into the system. If it comes into the system, then the entropy increases. If heat leaves the system, the entropy decreases. And dq is what we usually call Q, okay? So it's the same thing. And T here is the average temperature. In this case, we know the temperature is constant at 300. So all we got to do is find Q, isn't it? How much heat came in, and we know how to do that. Because we know that the change in internal energy is given by Q minus work, but because it's an isothermal process, the change in internal energy is 0 because there's no change in temperature. That means Q is equal to the work. Okay? Makes sense? These two must be equal. And we know the formula for work. Work is nRT, natural log V2 by V1. So if we find the work, we will get Q. N is 1, R is 8.314, natural log of, or you have the temperature and natural log of 1/5. Well, a natural log of 1/5 is going to be negative, so that makes the whole thing negative. When you multiply, you get negative 4014.3 joules. So now we have the heat, the work done. Remember, the work is negative. Why is the work negative? Because work is done on the gas. The gas is compressed. And when work is done on a system, it's negative. All right, so now to find that, because we already know work is the same as Q, ds is dq by T. So we have Q now, which is negative 401014.3 divided by T is 300. Divide them, and we will get the change in entropy as negative 13 joule per Kelvin when we look at the significant figures. So that's how we do that. Well, although I said that was the last problem, just want to do one more because this is a very important question. Question says 1 mole of an ideal gas doubles its volume in a reversible isothermal expansion. So it's 1 mole and the volume becomes double, so the gas is expanding, of course. What is the change in entropy of the gas? Let's do the A part first, and then we'll look at the B part. So similar to the last question, but not exactly the same. So V2 by V1 is 2, because it's expanding in this case. N is 1 mole, and change in entropy, ds is dq by t. It's isothermal again, so let's find the work, because the work will be the same as the quantity of heat. Here is the formula for work, and then, well, I'm trying to show you that this is 0, but we did the same thing in the last problem. That's why Q becomes equal to work. You already know that. So I just put the Q there. So Q is the same as work, and then I'm trying to directly work it out there, okay? And that means it's nRT, natural log V2 by V1 divided by T. The problem here is we do not have the temperature. But we don't need the temperature, because the temperature cancels out. So that's why I decided to put it into the formula to show you that we do not need the temperature. So then we get 8.314 times natural log of 2, which gives 5.76 joule per Kelvin. Okay, now the B part. If 1500 joules of heat are added in this process, what is the temperature of the gas? So when the gas is expanding, heat was also given to it, which is 1500 joules. Now we got to find the temperature of the gas. Let's do it. Okay. Q is nRT, natural log V2 by V1. The quantity of heat is given, so just make T the subject, rearrange, and calculate. Q is 1500, isn't it? 1500 divided by the number of moles is 1, so I've not written it. That's 8.314 natural log 2. And you get the answer. So it's 260.3 Kelvin. So this is a really important review on thermodynamics, where we looked at heat engines, refrigerator, heat pump, and change in entropy. So remember, there's another video where I worked out 10 problems, and you got to look at that video, and then the review will be complete. So there is a playlist called Thermodynamics. Be sure to watch all the videos in that playlist called Thermodynamics. All right? Hope you understood all these. We'll see you on the next video. Thank you.